All right, here's our warm up, and we're gonna fill out the table, and then we're also gonna write in some equations. So what I notice here in this first table is that oh, that's a little too thick there. The x values are increasing by 1, and if it's doing the same thing, I'm just going to put it in the same color there. I don't need to write +1 each time. And the y value right there, each time it's adding 3. And so each time the y value, if it's adding 3, this would be 14, and this would be 17. So that's filling out the table. In the bottom table there, again, we're adding 1. I don't need to write +1 because it's the same color. I'm showing that it's doing the same thing. And in the y values of the bottom table, I can't tell when I look at this first one what's happening. It looks like we might be adding 4, but then when I look at that, I can see, no, we're multiplying by 3. So we're multiplying by 3, and that's the way I'm going to write that. Multiplying by 3. Let's see, 3 times 50 is 150. 3 times 4 is 12. 150 plus 12 is 162. 3 times 160 is 480. 3 times 2 is 6, so it's got to be 486. Good morning, Jacqueline, Shep, Noah, Tommy. Good to see y'all. So, does anybody have any ideas here how to write the equations for for the first table? What's the equation for that first table? Just turn on your mic and start talking. I know someone out there knows it. No takers. All right. Well, since we are we're adding a constant amount each time, that tells me that it's a linear function, and Annika's got it there. So it's L of x is equal to 3 times x. And then we can see in our table right here, when x is 0, y is 2. So Annika's exactly right. L of x equals 3x plus 2. Great job. Questions on that one? Anyone have an idea for the second table? Does anyone know what kind of a function it is? It's not linear because we're not adding by the same amount each time. All right. Well, I'll tell you, since we're multiplying by 3 each time, we're going to have a 3. But because we're multiplying by 3, it's got to be 3 to the x. It's an exponential function, Annika. That's right. Great. And if you did the assignment yesterday, those notes, then you knew we're working on exponential functions now. And we can see here, because when x is 0, y is 2, this is going to be 2 times 3 to the x. So this is, you maybe saw this last year or sometime, but we're going to be working on these exponential functions now. Are there any questions for this warm-up? Okay. All right, Josh. So what was similar about the two tables? I'll go back to them so we can see them again. What was similar about them? Okay, so you're noticing that in the x's here and there, we're adding by 1. Yep. Okay, so in the upper table, you've noticed that we're adding 3, and in the lower table in the y values, we're multiplying by 3. So, Josh, I have a question for you here. Is there a way in which we could say in both tables there's a change of 3? Uh, yes. Can you tell me about that? So it's just that the word change means something different between the tables. Great. I love it. Thank you, Josh. So Jose claims that both tables change by 3 each time. So Josh agrees because change means something different in each table. Thanks, Josh. All right, we're going to pause the recording here. All right, what is similar about linear functions and exponential functions? Anyone here willing to share? What's similar about the two? Thinking about the equations themselves. Well, can we see the y-intercept in the two functions? Yeah, that's one thing that's similar. Whoops. Yeah, see the y-intercept and the change. Now the change is different between one and the other. One is addition, one's multiplication, represented in the equations. I think that's what you were saying, wasn't it? Okay. Awesome. I love it. What is different about linear functions and exponential functions? So what's the thing that's like the big difference here? How are exponential functions just one big thing that's different about them? The slope. So what do you mean, Holly? Yeah. Yeah. So I just wrote linear as a constant slope, but exponential changes. Is that the general idea I think you're getting at? Great. Thank you, Holly. What about in the equations? What's like the big difference in the equations? And I mentioned this in the video yesterday too. X is in the exponent for exponentials. Really had to squeeze that in there. Didn't do a great job. Can you tell the type of function from only 2 points? Why or why not? Anybody here willing to tell us about their idea here? If I just give you 2 points, can you tell me if it's linear or exponential? Thank you, Tommy. Can you say why or why not? No, you can't tell. Yeah, yeah, exactly. There isn't enough info. Great. So if we think about just 2 points like that, one equation could look like this, or one graph, that would be linear. And one might look like this, and that would be exponential. All right. All right. If a linear function is increasing, what can you conclude about the equation? So we have a linear function that is increasing. What can we say about the equation? And if folks just shout this out, we'll move much more quickly. There's part of the equation that we can say something about here. An increasing linear function. Well, m must be greater than 0. If an exponential function is increasing, what can we conclude about the equation? Well, y equals a times b to the x is the general form. If it's increasing, does anyone know what we conclude about the equation? B must be greater than, 1. B has to be greater than 1 if it's increasing. Why are the answers to the previous two questions different? Why is B must be greater than 1 and M must be greater than 0? Why can't B be 0? Well, when B is, here, let's do it this way. When B is between 0 and 1, the exponential function is decreasing. I feel like my writing is super sloppy today. I don't know if that's just me or if you guys think so too. What slope would create a line that is neither increasing nor decreasing? So if we're thinking about our y equals mx plus b again, so what slope would create a line that is neither increasing nor decreasing? What slope would create that line? 0. What growth factor would create an exponential curve that is neither increasing nor decreasing? So here, again, we're talking about y equals a times b to the x. If b is equal to 1, then really we just have y equals a, because 1 to any power is just 1. So this equation is y equals a times 1, which is just y equals a. And so that is just a line, a horizontal line, where a, y equals a. So this value right here, let's see if I can make this clear. This is a. That's really small. All right. Any questions there? All right. Depreciation. Some things exponentially decrease over time. This is called depreciation. Let's say you buy a car for $20,000, which decreases in value 0.1 or 13% each year. How much is it worth after 1 year? Well, oh, oh, yes, yes. So, Kai, so you said, isn't that an invalid exponential equation? Yes, it's not exponential, it's linear. You're absolutely right. Thanks, Kai. So, this is a little bit different. Instead of y equals a times b to the x, we're going to change that b here, and it's going to be y equals a times 1 minus a percent increase or decrease. And so I'm going to put just like a percent in there, percent symbol, and it's to the x. So here, the 13% is going to go right there. And our initial value is our a. And so we can write an equation, y equals 20,000 times 1 minus, and instead of 13%, we're going to write it as a decimal, which is 0.13 to the x. So x is the number of years, y is the value after that many years. So I'm going to pull out the calculator here, and let me bring up just the screen. So here we have 20,000, and then we're going to multiply that by 1 minus 0.13 is this. I can write it this way. I could also write 0.87. It doesn't make any difference, but we're going to raise that. We're asking about 1 year, so we just raise it to the first power at first, and it's 17,400. So here, after 1 year, so 1 year, whoops, 1 year is y is equal to 20,000 times 1 minus 0.13 to the first power, which is $17,400. Now we'll do 5 years. It's y equals 20,000. And this time I'm going to write 0.87 because that's the same as 1 minus 0.13. So now I'm going to do a little trick. I'm going to go up here and grab this and press enter, and that'll copy and paste it, and go in here and just change this to a 5. On the TI-84s, you can always do that. It's a pretty handy little trick. And let me get this out of the way. And so that will come out to be, wow, really close to $10,000. I'm going to put an estimate in here, and it's about $9,968.42. And finally, we'll do 10 years. Y is equal to 20,000 times 0.87. And notice that now we have a B value. And our B value is between 0 and 1, which means we're depreciating. So when the B value here is between 0 and 1, we're have an exponential decrease here. So a depreciation is an exponential decrease. So now I'm going to go up and grab that and change that 5 to a 10. And we get about $4,000 or $5,000. Oh, look at that. Whoops, I should add a 10 there. That is interesting. So Does anyone notice anything about these values we chose for the number of years and the value of the car after that many years? Anyone notice anything? From 0 years, $20,000, to 5 years, it about halved. From 5 years to 10 years, it about halved again. If you remember in science, that's called a half-life. So the half-life is about 5 years on this depreciation with 0.13 as the depreciation. Yeah, thanks, Kai. Exactly. All right, now we're going to have a look at appreciation here. So again, we're going to use the y equals a times 1 minus the percent to the x value. So here we have an investment of $2,500, and that's going to be our A value. And the rate of appreciation is 5% each year. Okay, so our equation then is going to be y is equal to $2,500 times 1 minus, and the percent is 0.05. Remember, move that decimal over 2 places to, it's from 5 to 0.05 in order to convert there. And we're raising it to the x. So that's our equation we can use. Now for 1 year, it's going to be y is equal to 2,500 times, and I'm just going to say 1.05. Notice that now our b value is greater than 1, which means we have an exponential increase. So with our initial investment of $2,500 at a rate of 5%, after 1 year, it'll be $2,625. So $125 of interest in 1 year. For 5 years, y equals 2,500 times 1.05. Whoops, I didn't do something. I should have changed this to a 1, not a x. Sorry about that. So in this case, again, I'm going to go back up, take a shortcut because mathematicians are like that. And it's going to be about $3,190.70. And lastly, for 10 years, we have y is equal to 2,500 times 1.05 to the 10th. And that will come out to be about $4,072.24. So you have an increase after 10 years of about $1,500. And that is it for today. There is a link on our Canvas that I'll show you. And if you want to do a little bit of extra work, you can go do these practice problems right here. I'm going to paste in the exit ticket for the day. And if you could fill that out, I'd greatly appreciate it. Well, that's our first class done for the new semester. I hope it's a good one for you guys.